Let's jump right in. Welcome to today's explainer. We're tackling a critical component that quietly, yet literally, powers some of the most intense industrial operations on the planet. Our main goal today is to answer one huge question. What exactly is ASTM A106 steel pipe and where do we actually use it? We're going to break down the technical specs, the chemical DNA, and the real-world scenarios where having this specific material is absolutely non-negotiable.
Okay, let's dive into this. Just imagine a working environment that would melt, warp, or completely destroy your standard everyday materials. We are talking about extreme, sustained, high-heat environments here. Systems that have to operate continuously at temperatures pushing 650 degrees Fahrenheit. That's roughly 350 degrees Celsius. When engineers are designing systems with those kinds of intense thermal demands, ordinary pipes simply won't cut it. They absolutely need a specialist.
So, here's our structural roadmap for today. First, we'll meet the high-temperature specialist itself. Second, we're unpacking the chemistry and specs. Third, the ABCs of grades. Fourth, we'll weigh A106 against the alternatives. And finally, making the right choice in the field.
Section 1. Let's meet the high-temperature specialist. When we ask, what is ASTM A106, the answer is actually hiding right there in its official title. Standard specification for seamless carbon steel pipe for high-temperature service. Every single word in that title was carefully chosen, but two terms are absolutely non-negotiable for us: seamless and high temperature. This isn't just some generic piece of steel you grab off a rack. It is a highly engineered product built specifically for a demanding, brutal environment.
Because A106 is seamlessly manufactured, it completely eliminates the welding seam. And why does that matter? Well, under extreme thermal stress, a welded seam can easily become a dangerous point of weakness, which can lead to a catastrophic failure. By removing that seam altogether, A106 becomes the ultimate implant solution. It is exactly what you want for steam lines and power plants, handling fluids well over 300 degrees Celsius, refinery boiler feedwater lines constantly battling pressure, and chemical plant production lines moving incredibly hot liquids and gases.
Section 2. Unpacking chemistry and specs. Let's look under the hood.
Now, what's really interesting about this slide is that we are looking directly at the authentic ASTM standard document. It's not a summary. This is the actual Table 1 detailing the chemical requirements. It maps out exactly what elements and in what precise percentages must go into the steel to actually earn that A106 designation. And you know, there is one element in particular that acts as the real unsung hero here. That hero? It's silicone. ASTM A106 mandates a minimum of 0.10% silicone. This is the crucial alloying element that gives this carbon steel its literal superpower. Without this specific addition of silicone, regular and continuous exposure to extreme high temperatures would just slowly degrade and weaken the pipe over time. Silicone is the secret ingredient that locks in that high heat resistance. It's a real game changer.
Beyond the silicon, the manufacturing specs are incredibly rigorous. The steel has to undergo a killed steel primary melting process, which basically means it's completely deoxidized to ensure maximum structural uniformity. Also, if the pipe happens to be cold-drawn during manufacturing, the standard strictly demands it undergo a heat treatment of at least 1200 degrees Fahrenheit or 650 degrees Celsius to relieve any internal stresses. And here's a fun fact. While we normally think of sulfur and phosphorus as impurities to avoid at all costs, trace amounts are actually intentionally allowed here. Why? Because they significantly improve the steel's machinability.
Moving on to Section 3, the ABCs of grades. A106 isn't a one-size-fits-all situation. And this brilliantly illustrates how the specification is tiered. We can see a very clear ascending progression of minimum tensile strength. Grade A sits at 48,000 psi, Grade B steps it up to 60,000 psi, and Grade C pushes the absolute limit to 70,000 psi. But this increase in strength doesn't just happen by magic, right? It comes down to a very specific, deliberate chemical adjustment.
The key variable we're tweaking here is carbon. Grade A limits carbon to a maximum of 0.25%. Grade B allows up to 0.30%, and Grade C bumps that up to 0.35%. So it's your classic engineering trade-off. As carbon content goes up, the steel gets stronger, allowing it to withstand much higher pressures. However, that added strength comes at a cost. As strength goes up, the ductility, meaning the pipe's ability to bend, and its overall weldability actually go down.
So, to keep it simple when you're out in the field, just remember this rule. A to B to C means increasing strength.
C is the strongest and most rigid, while A is the softest and easiest to form. Because of this trade-off, Grade B is overwhelmingly the industry standard. It hits that perfect Goldilocks middle ground. It gives you a really robust 60,000 psi tensile strength while maintaining enough ductility and weldability for your standard fabrication work.
Section 4. A106 versus the alternatives. Because knowing what A106 is requires knowing what it isn't.
Let's look at its most common cousin, ASTM A53. So the crucial point is that while these two carbon steel pipes might look totally identical sitting next to each other on a rack, they are built for entirely different worlds. A106 is completely seamless and relies on silicon for intense heat applications, like power generation. A53, on the other hand, it can have a welded seam and contains absolutely zero silicon. If you put A53 into an extreme high heat environment, it is highly likely to fail on you. A53 is designed for low to medium pressure transport of air and water or to be used as structural steel. It is not a high temp player.
Then we have API 5L. Again, they look super similar, but their domains are strictly separated. Remember, A106 is an in-plant process pipe. Its entire existence prioritizes surviving internal heat up to 650 degrees Fahrenheit. API 5L, though, is the long-distance expert. Its job is to form those massive cross-country oil and gas pipelines spanning hundreds of kilometers. It prioritizes external durability against soil movement and the ability to be manufactured in huge diameters.
Now this highlights exactly where the danger lies. Take a look at the yield and tensile strengths for A106 Grade B compared to API 5L Grade B. They are completely 100% identical at 35,000 and 60,000 psi. If a buyer only looks at the baseline mechanical strength on a sheet, they might think, oh, these are interchangeable, but they absolutely aren't. API 5L does not have the mandatory 650-degree high-temperature rating. Swapping API 5L into an A106 system is a direct code violation and, frankly, a massive safety hazard.
Section 5. Making the right choice. Let's get into the actionable takeaways.
If you take only one single thing away from this entire explainer, let it be this absolute golden rule. Overlapping mechanical properties do not equal interchangeability. I'll say it again. Just because a spec sheet says two pipes share a 60,000 psi tensile strength doesn't mean they will survive the exact same environment. You always have to consider the heat rating, the underlying chemistry, and the manufacturing process. Let's move to our buyer's bottom line and see how this builds a rock-solid procurement strategy. First things first, never, ever substitute A53 or API 5L when the design explicitly calls for A106 in a high-temp system. Second, don't just order generic A106. Specify exactly whether you need grade A, B, or C based on your pressure and weldability needs. Third, before any fabrication even begins, always verify the Material Test Certificate or MTR. That document is your ultimate proof of the pipe's true chemical and physical properties. And finally, maintain detailed procurement records to ensure total clarity across your entire supply chain. So as we wrap up today's explainer, I want you to think about your current or upcoming projects. Are your blueprints and specifications truly crystal clear? Or are you risking a catastrophic failure by playing a dangerous guessing game with your piping materials? Take the time to review your specs, consult the ASTM standards, and ensure you are deploying the exact right tool for the job. Thanks for joining me to break down ASTM A106 and keep building safe, reliable systems out there.